Welcome to the final week of remote learning for the 2019-2020 school year. This week, our topic is a nonlinear review. Last week, we did a linear review. Your homework for this week will be another Desmos activity, and I will give that code at the end of the video. And my office hours this week are Monday through Friday from 1 to 2. But again, I did a couple Google Meets last week with some students, and again, I'm happy to support you, so just let me know. Okay, today's review is going to start out with some properties of exponents review. Some of you figured out rules or formulas that you can use for these. So I'm going to address those first. Again, I'm not a fan of rules and formulas, so when I work through the actual examples, I'll probably try to write most of those out. So the first one is a to the 0, and if you remember, anything to the 0 power equals 1. On your calculator or in Desmos, you can also do that. Type in any number, raise it to the 0 power, press enter equals, and you will see that it gives you 1. The second example here, it says a to the x times a to the y. And if you remember from earlier this year, that is considered multiplying like bases. And we multiply like bases, we add our exponents. So that would be a to the power of x plus y. The third example is when you raise a power to a power, so a to the y all raised to the x power. And when you raise a power to a power, you multiply your exponents. So that would be a to the yx, or xy if you prefer. The next one, we are dividing like bases, a to the x divided by a to the y. And when we divide like bases, we subtract our exponents. And then last but not least, we have a to the negative x. And when you're given something like a to the negative x, we think of negative exponents. Those are they're not okay, they're not defined. We need to fix them. And if you have a negative exponent, then you need to move that. So this one is in the top. So I'm going to move it to the bottom, and it becomes 1 to the a over x. If that negative exponent had been in the denominator, then we would have moved it to the top, called the numerator. Again, these are your rules. To me, the two that we kind of have to know as rules are the first one, that anything to the 0 power is 1, and this last one, that if we have a negative exponent, we have to flip it and make that exponent positive. The ones in the middle, we can pretty much get around those just by writing the problem out. All right, so let's look at some examples here. The first one says a to the third times a to the fifth. And again, I'm going to write this one out. So again, remember a to the third means a times a times a. And then a to the fifth would be a times a times a times a times a. Squeeze that in there. And so if we look at it, how many a's do we have altogether? There are 8 of them, and they're being multiplied. So instead of saying a times a times a 8 times, we can just simply say our answer is a to the 8th power. Again, if you are the one that likes to use the rules, we are multiplying like bases, so we add our exponents. So that gives me a to the 8th. For the second example, we have c to the 5th divided by c to the 7th. So for the top part, the little red dot up there, I've got 5 c's on the top. And I'll put a little blue dot on the bottom. I have 7 c's on the bottom. And then if we have a c on the top and a c on the bottom, those divide. C divided by c is 1. C divided by c is 1, 1, 1, 1. And so we notice some kids want to say there's nothing left on the top, but technically there's a 1 up top. And so we have a 1, and then the bottom we have c times c, which is c squared. Again, if you would like to use the property that says when you divide like bases, you subtract your exponents. You can do that. 5 minus 7 is going to give us a -2, but then we would have to use that property that says you've got to make the exponent positive, and that would require you to move it to the bottom, which would give us 1 over c squared. So in the next example, this one to me is kind of tricky because you have 2 negative exponents. So I'm going to do the inside part first, which is g to the -3. So that becomes 1 over g cubed, but then that's raised to the -5th power. And then remember, if it's a negative exponent, we're supposed to flip it, so we have to flip everything inside that parentheses. So the g cubed would now come back up to the top. We can put the 1 on the bottom, and then the exponent becomes a +5. And then when we raise a power to a power, we multiply, but remember that means g cubed times g cubed times g cubed. So that would be 5 times. And so we have 3, 6, 9, 12, 15. So my final answer would be g to the 15th power. And you could put that over 1 if you wanted to, but it's not necessary. All right, in our next example, we have 3x squared squared. Remember, to square something means multiply it by itself. So that would give me 3x squared times 3x squared. So again, taking that square. And then numbers are numbers. So that's a 3 times a 3 would give us 9. And then if we look at the x squared, remember there's 2 x's here and 2 x's here. So x squared times x squared, we've got 2 x's there and 2 x's there for a total of 4 x's. And since we're multiplying, that would give us 9x to the 4th. All right, for our next example, it has xy to the 4th squared and 2x cubed cubed. So remember that xy to the 4th squared, I would have to write that one down 2 times. And then the second one, I would have to write that one down 3 times. Now again, all these are being multiplied. My box is too small for me to include all this on one row. Oh, hold up. I'll put those 2's in there. Sorry about that. So I have xy to the 4th squared, which is xy to the 4th times xy to the 4th. And then I have 2x cubed, and so I wrote that one down 3 times. Remember that there are 1's in front of this xy to the 4th. So if we multiply all of our numbers, 1 times 1 times 2 times 2 times 2 would give us 8. And then we have, if we look at our x's, and I'm going to use my highlighter for these, we've got 3 x's here, 3 x's here, 3 x's here, because remember that's x times x times x, so that gives me 9 x's. Then we have 10, and we have 11. So we could write that, I think we said, let's see, 3, 6, 9, 10, 11. So that's x to the 11th power. And then if we look at our y values, we've got a y to the 4th and another y to the 4th. So there's 4 y's in one and 4 y's in the other. And so that is going to give me y to the 8th power. Again, you could use your properties of exponents as well. To come up with that answer. All right, the next one says -12 to the 0 power, and this is a really tricky one. You have to remember that that -12 is really a -1 times 12 to the 0 power. And so it's kind of splitting that up into 2 pieces. Notice the negative is not in parentheses. So the 12 is actually the only thing that's being raised to the 0 power. So that gives us a -1. Anything to the 0 power is 1. So my answer is -1. I'm going to switch up the order and go right underneath this to -12 to the 0. So in this case, -12 is being raised to 0 power. So this answer is just a +1. So note the difference in the two. Outside of parentheses, if we just have a negative and then 12 to the 0, that simplifies to a -1. Whereas if the -12 is in parentheses, then we get a +1. I think we'll just continue going back in the opposite direction. So let's take that question in the middle. So again, numbers are numbers. So we're going to take the 2 times the 3, which will give me 6. And then we have x to the 5th. So that would be 5x's, and x to the 10th, which would be 10x's. So that would give me a total of 15x's. So 16x to the 15th, because 5x's and 10x's give you 15. All right, and the last one for this example, we have g to the 5th times g to the -9. And since we can't have negative exponents, I'm going to move the g to the -9 to the bottom. And that exponent becomes positive. And then remember, I would have 5g's on the top and 9g's on the bottom. And then g divided by g is 1. Let's switch to a color. And so we're left with, again, some people say there's nothing on the top. There's really just a 1. So we have 1 over, and then g times g times g times g. Since there are 4 of them, that would be g to the 4th power. So as you can see, I prefer to write everything out when possible instead of using the rules that we looked at on the previous slide. All right, we're going to review some exponential functions right now. So here we're given a table, and we want to write the exponential function from the given table. So if you remember my favorite, one of my favorite questions or lines from this year was, where do you start and how do you change? And again, you may remember me saying, how old were you when you started life? So for this first question of where do you start, we look at our start is at time 0. So we started at 5. And then if we want to look at our change, we have to look at the pattern here. Notice the x's are counting by 1, and we have to figure out what are happening to our y values. And this is called e of x, but again, that's just the same thing as y. So how do I get from 5 to 10? Well, that doubles. 10 to 20, that doubles. And that pattern continues. So we are changing by multiplying by 2. So we can write our equation. Y equals, where do we start? We start at 5. How do we change? We're multiplying by 2. And remember, because we are multiplying, then we have repeated multiplication is what gives us the exponent being the x. So we have written an exponential equation. So 5 times 2 to the x. All right, so here's another example with a table, and we're going to write the exponential function. So again, our favorite 2 questions here. Where do you start? And how do you change? Again, you started life. When you started, you were 0 years old. So you look in your table at 0, and we see that we started with a value of 64. And then we want to figure out how we change. And this one's a little tricky. The last one was kind of straightforward, but this one kind of scared me a little bit because I'm like, how do I get from 64 to 48? How do I get from 48 to 36? How do I get from 36 to 27? That last one's super scary. But if you remember, we can tell the numbers are getting smaller, and you can always take a term and divide it by the term before it. So for instance, 48 divided by 64. And then if we simplify this, we will get 3/4. Both 48 and 64 are divisible by 16. Now you may think, well, why did you use those two numbers? Well, I could have done the 36 and the 48. So I could have taken 36 divided by 48. Actually, I'm a little bit more comfortable with this one doing it in my head. Both of those are divisible by 12. So I could simplify that to 3/4. But again, how do we change is the 3/4. We are multiplying by 3/4 each time. Last time I wrote y. Again, this is the same thing as y, but we can practice using that function notation. So I can call it p of x. We started at 64, and then we multiplied by 3/4 each time. And since there was repeated multiplication, we have our x as our exponent. So hopefully that's a refresher on writing exponential equations. All right, so next we're going to look at the graph of an exponential function, and then we're going to evaluate that exponential function for a specific value. So this one says f of x equals 27 times 1/3 to the x. So we could just make a little table. And yes, you know I love tables. So we could just plug in a few numbers here, 0, 1, 2. We'll see if that's enough. Again, anything to the 0 power is 1. And so when we plug in, we would get 1/3 to the 0, which is 1. So I would get 27 times 1, which is 27. If I plug in 1, that will give me 27 times 1/3. So 1/3 of 27 would give me 9. And then 27 times 1/3 squared would be a 9th. And again, you could use your calculator to evaluate these. And then 27 times 1/9 is going to give me 3. And if we wanted to do one more, I guess we could go ahead and do 3. So 27, and then if we do 1/3 cubed, so 1/3 times 1/3 times 1/3, that's going to give me 1/27th, and that equals 1. So given this sheet of graph paper, it's going to be a little bit difficult to graph this since 0 is equal to 27. So obviously I'm not going to count by ones. It's not going to fit. I probably don't want to count by tens because that's going to make our graph really small. But I guess we could count by fives. So we'll say that this is 10, this is 20, and this is 30. For my x-axis, I'll just count by ones. So again, our graph is a bit distorted, but again, I picked the scale I wanted. And so I'm going to plot each of those points as best I can. So 0, 27 would fall somewhere about there. 1, 9 would be about right there. 2, 3, say about right there. And 3, 1. And so this is our exponential function. I believe my first one disappeared here. Let's put that back. So 0, 27. Some of you call these J curves. Before I draw this curve in, if we think about this for a second, if I take 27 times some number, so 1/3 raised to a power, it's never going to be a negative number. That's going to get closer and closer to 0. And again, you could look at your table in your calculator, or you could continue plugging in values, but this graph will just continue to get smaller and smaller and smaller, approaching 0. And here this graph will continue going up. And we could plug in some negative numbers there if we wanted to. Sorry, my graph is a little messy. And speaking of, that's what our evaluate says. Find f of negative 2. So f of negative 2 is essentially saying where there's an x, replace it with negative 2. So 27 times 1/3 to the negative 2. And again, we know we can't have a negative exponent, which requires us to flip the fraction. So it becomes 3/1 squared. So that's really just 27 times 3 squared. And 3 squared is 9. And so lastly, if we multiply 27 times 9, that gives us 243. Actually, there's no way I was going to be able to fit that on my graph, but I did want to remind you about how to evaluate an exponential function with a negative exponent. All right, so here's another one. This one is 10 times 2 to the x, and then later on I'm going to ask you to find g of 6. So again, we'll just start with our handy dandy table. So I can start with my 0, 1, 2. If I plug in 0, anything to the 0 power is 1, so that gives me 10. If I plug in 1 for x, 2 to the first is 2. And if I plug in 2 for x, 2 squared is 4. So that gives me 40. So 10, 20, and 40. Again, I think counting by fives is probably okay given the numbers that I have chosen. So we'll call that 10, 20, 30. It's going to go a little off the page, but that's okay. And so now if we plot those points, 0 is 10. And by the way, I'm still counting by ones on my x-axis, just like in the previous example. And usually say it's understood that you're counting by ones unless you specify otherwise. We would plot the point 2, 20 and 3, 40. Again, I know this is exponential, so I know that curve is going up. And then I know it continues down. Again, it's never going to become negative because I can't raise 2 to any power and get a negative number. The last one asks us to evaluate g of 6, which again is off of my graph. So g of 6 means replace the x value with a 6. So 10 times 2 to the 6th. Remember, 2 to the 6th means 2 times 2 times 2 times 2, 6 times, and that gives us 64. And so that value would be 640. So again, way off of my page. And so that's a review of graphing exponential functions. All right, and the last thing that we're going to review, which is something we did during remote learning, and that is factoring quadratics. I'll put some special cases in here. Tried to give you kind of an example of everything that we worked on. So the first one is x squared minus 144. And if you remember from the video, I told you could write that as x squared plus 0x minus 144. And then we can make our little box. We can fill in our x squared, our negative 144. And again, we're trying to figure out what multiplies to give me negative 144 and what adds up to give me 0. And that would be a 12 and a negative 12. Again, this is a difference of squares. Again, I did not include the x, so I'm going to do that now. So the 12x and the negative 12x, again, it does not matter which one goes in which spot. X times x is our only option, thinking back, way back to our duck pin. Again, if this side is x, the right side will be x. If the top is x, the bottom will be x. And now it's just a puzzle. X times what gives me 12x? That's 12, so I can put a 12 on the bottom. Moving to the second row, the negative 12x, x times that would give me a negative 12. So this would be negative 12. And that bottom right-hand box is your check box. 12 times negative 12 does give me negative 144. So my two linear factors, again, it's been a while, are going to be these two dimensions. And so my two factors for this problem would be x plus 12, and x minus 12. All right, let's look at letter B. This one has a middle term, x squared minus 3x minus 28. So I'm going to go straight to drawing my blocks. Go ahead and fill in the x squared and the negative 28. Again, I'm trying to just remember one thing I didn't do on the last one. We always talk about what multiplies to give me this diagonal. And when I multiply that, that's going to give me a negative 28x squared. So I'll include the x this time. And then I want to see what's going to add up to give me that middle term. And that middle term was that negative 3x. And so if I think about what multiplies to give me negative 28 and what adds to give me negative 3, obviously I'm going to have a positive number and a negative number to be able to get a negative 28. And I think that's one that I remember from my multiplication tables back, I guess, in 3rd grade. So that would be a 7 times 4 would give me a 28. But I need a negative 28, and I need to add up to get a negative 3. So that would be a negative 7x and a positive 4x. Again, it doesn't matter which one goes in which block. And I didn't leave myself much room here. Let me erase the line there. So x times x goes on the bottom, x goes on the far right, x times, that would be a negative 7. I can put that at the bottom. Second row, x times 4 would give me 4x, move that over. In the bottom right hand corner, make sure that's right, negative 7 times 4 would give me a negative 28. So my two factors, again, come from the sides. These are our dimensions. So we have an x minus 7 and an x plus 4. All right, letter C is one of the harder ones because that leading coefficient is not 1. And the only reason I say it's harder is just because the numbers are a little larger. But again, I haven't mentioned this because I've looked at all of these and none of them have had a leading coefficient that wasn't 1. And not every term had an x in it, so I knew there was not a GCF, a greatest common factor. But in this problem, since there's a 6 out front, I did kind of, in my mind, look through and notice that they were not all divisible by 6, nor were they all even or divisible by 3. So I don't have a GCF. So I'm going to just jump straight into making my block, filling in my 6x squared and my negative 10, making my x. Again, I want to see what multiplies to give me, and that would be a negative 60x squared. I think this time I'm just going to write the negative 60 for space. And then using that middle term, I want to add up to negative 11. Again, this is a little bit harder if we start thinking about the factors of 60. 1 and 60 is not going to work. 2 and 30 is not going to work. 3 and 20 is not going to work. But I believe 4 and 15 will. 15 times 4 would give me 60. And if I subtract 15 and 4, that would give me 11. But I need a negative 11. So I'm comfortable with a 15 and 4. But I need to multiply to get a negative 60 and add to give me negative 11. So that would be a negative 15. When I go back and write these in, again, I have to include my x. And so now we need to find a GCF. With a GCF, remember, it doesn't matter if you use the row or the column. I think in those earlier videos, I was kind of a fan of using the row. So I'll stick with that here. Oops, let's choose. Maybe this will show up a little bit better. So 6x squared and negative 15x. So what are 6 and negative 15 both divisible by? I believe that's 3. and they both also contain an x. So if I've got my 3x there, that means I would put a 3x on this side as well. So 3x times what gives me 6x squared? So that's going to be a 2 and an x. And I can put that 2x on the bottom. And I can say 3x times what gives me negative 15x, and that would be a negative 5. Put that on the bottom. Then going to the second row, 2x times what gives me 4x, and that would be 2. Put the 2 here, double check, is negative 5 times 2, negative 10, and that is. So my two factors are, let's see, the 2x minus 5 and that 3x minus 2. Hopefully that blue isn't too, or I think I said 3x minus 2, it's a 3x plus 2. Again, a little bit hard to read, but those two factors are 2x minus 5 and 3x plus 2. So that is my factored form. All right, and last but not least, and I kind of felt like maybe I left the easiest one till the end. This one just has two terms. Remember in letter A we only had two terms, but there was not a GCF for that one. But in this one, we have 72x minus 9x squared. So I immediately see that they both have an x term, so I know there has to be a GCF. And then when I look at the 72 and 9, I believe both of those are divisible by 9. So we're going to factor out that GCF, which would be a 9x. And then 9 goes into 72 8 times. We've already taken out the x. And then a negative 9 divided by 9 would just be a negative 1. So you can put the 1 if you would like, and then an x. Or again, if you prefer, you can just write 9x times 8 minus x. Typically, that's how you would see it on a standardized test. So that wraps up our review for today. And now it's time for you to do some practice. So if you have run out of paper at this point, you'll probably want to get a clean sheet to work through some of these practice problems. Again, I will want you to pause the video as you're working, work out the problems, and then push play when you're ready to check them. On these, I'm just going to supply the answers instead of all the work, but if you have questions, please send me an email and I'm happy to work them out in a Google Meet. Okay, for your first practice problem, I ask you to simplify each of these expressions. There are 5 of them listed. So at this time, press pause, work through these 5, and then when you're ready, press play, and then I will show you the answers. Okay, I'm going to move on to the next slide with the answers. So again, if you're not ready, press pause. Okay, here are the answers. For letter A, anything to the 0 power is 1. For letter B, you had a negative exponent, which you had to move to the bottom and then simplify. It gives you 1 over x to the 4th. Letter C, the 5 times 7 gave us 35, and then we had a total of 13 x's, so x to the 13th. Letter D may have freaked you out because there were numbers instead of variables. Works the same way. You have 17 threes on top, 10 17s on the bottom, so 3 of them will cancel out, and you're left with 7 17s on the bottom. And then for letter E, you're squaring something times itself. So 3 times 3 gave us 9, and then we would have 3 x's and 3 more x's for a total of 6 x's. Again, if you want me to work any of these out, please send me an email. All right, so for question number 2, it says write the equation for the exponential function described in the table below. This one might be a little bit harder than the examples that I worked, but give this a shot. And again, when you're ready, after you've got this one completed, then you can press play again to continue. All right, if you did not press pause, please do so at this time. If you're ready, I am going to move on. So I tried to actually show my work a little bit on this one. This table did not show the starting point of 0. I noticed that in the table we are multiplying by 1/4 each time. I guess I could write a little bit more of those in. So each time we are multiplying by 1/4. So I'll work backwards, and if we were multiplying by 1/4 to work backwards, or you could say divide by 4, working backwards we would be multiplying by 4. And so that kind of helped me figure out that that initial term, my starting value would have been 160. That requires more work, so you could have definitely gone straight to the green answer, which is just using the information from the table. I saw that the table started at 40. I was multiplying by 1/4 every time, and since my table started at 1, my exponent was x minus 1. Again, it's been quite some time since we've gone over that, so you may have forgotten. Okay, here's our third example, our third practice problem. So I want you to graph this exponential function and then evaluate. So we have 16 times 1/4 to the x, and then evaluate e to the -2. Again, you pick the scale that you want, keeping in mind that it probably won't match mine, but the scale is up to you. So again, press pause, work through this, and when you're ready, press play. Okay, I'm going to move on to the next slide to look at the answer. So for my problem, I chose to count on the x-axis by ones. And then I guess technically on the y-axis, I was counting by 2.5. I just labeled every other. So I showed 5, 10, and 15. I made my favorite table. I just plugged in 0, 1, and 2, plotted those points. Again, this is exponential decay. It's decreasing, reading left to right. And at the bottom, I showed you how I plugged in the -2 for x. Again, a negative exponent requires you to flip your fraction, so then it became a positive 4 over 1 squared, which was 16, and 16 times 16 gives us 256. And our last example is factoring. These are 4 questions similar to the 4 that I worked with you, so you could maybe use those as a guide. So again, if you'll press pause, work through these 4, and then when you're ready, press play to check your answers. All right, I'm going to continue now. If you're not ready, please press pause. So here are the 4 answers. Letter A is x plus 9 times x plus 3. Letter B was a GCF. You had to factor out the 5x, and then you're left with x minus 3. Letter C was a difference of squares, so you end up with x plus 20 and x minus 20. And then letter D, that's one of the harder ones where that leading coefficient is not 1, and we don't have a GCF, and our factors end up being 4x plus 1 and x minus 3. Again, feel free to reach out if you would like for me to work through any of these with you. I'm happy to do so. So as crazy as it may seem, that wraps up our 2019-2020 school year. One last activity for you. Again, it's a Desmos activity. So if you'll go to student.desmos.com, again, make sure that you are using your Wake County Google account, and the code is AMCZPT. I hope you've learned a lot this year. I've enjoyed working with you guys, and please stop by and see me next year. Have a great summer.